So, in this lecture today we are going to continue from what we were discussing in the last class regarding the idea of this LES and the LUS and how that can be used to model, considering an analog of the ideal fixed bed adsorber, or when there is no mass transfer zone, which of course does not exist in the reality, but using this idea of LES and the LUS, one can consider an analogous version of the ideal wavefront of a non-ideal system where there is finite width of the mass transfer zone. Now, in this case, let me quickly remind what do we mean by the LES and the LUB. So, LES represents the length of the equilibrium section. LUB stands for the length of unused portion of the bed. MTZ represents the mass transfer zone here. So, typically if this is an adsorption bed and this is the adsorption front, so this is like the equilibrium portion. So, this is LES. This is the unused portion. So, this is LUB, and in between these two we have the portion of the mass transfer limitation, or the mass transfer zone, or the active zone of adsorption, where all this dispersion, adsorption, kinetics, diffusion, transports, etc. takes place, mass transfer zone. So, this is like a this is like a system where and in the case of an ideal scenario, this adsorption front is actually like a shock wave. There is absolute plug flow and all the ideality conditions are maintained. Then it is reasonable to approximate there is mass transfer zone is 0. So, this is like the equilibrium portion and this is the unutilized portion. So, in both of these scenarios we consider this is like inlet and this is outlet. So, this is in, this is out. So, let us try to use this idea that in the case of when the mass transfer width is non-zero, there is a finite width, we consider halfway in between. So, that half, from that half we consider the remaining portion of the bed on the downstream side as the unutilized portion, and on the upstream side of the inflow is considered as the equilibrium section. Now, let us try to look into an example problem, and as this is best understood with the help of a example. So, this is a sample profile of the breakthrough plot. So, here this left hand side represents the C in by C out, and the this x axis represents the time in hours. So, this is a particular experiment of adsorption in vapor through a fixed bed. The inlet concentration of this vapor is around 600 ppm of adsorbate, although that is not very important in this case, that information, but still for the knowledge I am writing it down. Is the relative ratio with respect to the output to the input is what is important. Now in the output section, the first thing that it should be understood is that what is the sort of the this breakthrough time that one can consider. So now in this case, the breakthrough time can be considered to be the point when the this value or this value of C by Cf reaches a particular level that I was referring to in the last class. So for example, in this case, let us identify this point, something like 1% of the inlet can be considered as the point when the bed no longer actually performs or delivers desirable output below the permissible value, can be considered as the breakthrough time. So this breakthrough time, in this case, let us assume or let us consider this point, the black dot. So it is roughly around 3.65 hours in this problem here. Of course, depending on what is the level of concentration, if someone wants to set the level of concentration here in this case as something like 0.2, then the breakthrough time would be different. But whatever it is, the breakthrough time is the point when we consider that this is just the onset of the sigmoidal curve starting from a non-zero value, which could be like 1% or less than 1% depending on what is the level of output that is desired. Now the next question for this using this curve that you can work out is that what is the usable capacity of the bed at this breakthrough time if an ideal, let me write it down, what is the usable capacity of the bed at this breakthrough time if we had ideal wave front. Which means that there is no mass transfer resistance. So in this case, the ideal wave front capacity would be the ratio of the shaded areas of A1, particularly on the onset of the breakthrough time with respect to the total area. So what I mean here is that one can consider an ideal breakthrough time or the ideal this wave front. In that case would be essentially the breakthrough curve or the shock wave curve in that scenario would look something like this. At the breakthrough time it reaches the sigmoidal it reaches to the value at equal to 1. So this would be like if we are considering that the bed attains breakthrough right at the breakthrough point, then what is the usable capacity? So in that case one can, if you see here, the capacity of the bed, the total capacity of the bed or the capacity of the bed or the utilization of the bed, capacity or utilization of the bed at any time t is represented by the area of the curve with respect to the time. So the capacity of the bed can be represented as whatever the outlet concentration that is achieved, right. In this case, that would be, in this scenario, the amount of the species that is adsorbed, which is actually removed from the solution, can be represented by whatever the outlet concentration what one gets minus the inlet concentration. Sorry, this would be 1 minus C out by C in. Of course, multiplied with the volume with respect to time, 0 to time. So, this is like the amount of the material or the amount of the adsorbate species that is actually removed over this time. So, this is essentially what is contributed. So, from this ratio of this 1 minus of C out by C in, sorry, this should be C out, I wrote this wrong, with respect to C in, that is how we relate it from 0 to 1. So, in this case this is like the amount of the solute that is actually removed from this system. Of course, this has to be multiplied with C of in. That is what I mean, that the difference in the concentration and how much of the fraction that is removed is represents the capacity of this bed. Now, in some way this is linked to the portion of the shaded area. So, the shaded area reflects the capacity of the bed, or at least the fractional capacity of the bed can be related with respect to the shaded area here, like the area of A1 by with respect to this area present here. Now, in this case, since we are considering it to be an ideal wave front, so the area of the rectangle of this portion before it reaches breakthrough and after it reaches breakthrough in the non-ideal scenario, the ratio of these two time would be sufficient enough. So, in this case the breakthrough time here, in the case of this ideal wave front, or the breakthrough time that it is considered, let us consider this as like the TB, and this is like the saturation time when the bed has reached almost this saturation limit. In this case this is around 6.9. So, in this case of this ideal scenario, this capacity, instead of doing this integration under this curve, since this would be like the square areas or the rectangular areas, this capacity here, usable capacity for the ideal wave front, can be related to the ratio of these two times as TB by TS, and in that case this would be 3.65 by 6.9 hours, which is roughly equal to 53%. So, considering an ideal wave front, and since this in this case, since the area of this rectangular square, whatever the other unit is like unity, so one can easily represent, instead of considering the area, you can easily consider the time or the ratio of these two time when it reaches saturation and when it reaches breakthrough in the instance of ideal wave front. This can be related. Now, the next point is what is the actual fraction. Now, if we do not have this ideality condition, what is the actual fraction of the bed capacity which is used at this breakthrough. So, the question is next, what is the actual capacity of the bed used at this breakthrough condition. So, in this case, first we have to find the actual capacity from the total shaded area represented by this A1 plus A2. Now, of course, this A1 plus A2 represents the stoichiometric capacity. The stoichiometric term is actually evolved from the fact that this is like the mass balance or the total amount of the capacity of the bed that it can absorb should be equal to the this the amount of the species, the mass of the species that is removed from this system, which is nothing but equal to the inlet concentration times the volumetric flow rate that gives us with and multiplied with the time, that gives us what is the amount that is removed, and that is equal to the equilibrium capacity. That is why it is related to as the stoichiometric capacity. So, if no mass transfer resistance was there, then this stoichiometric time Ts can be taken as the time taken for this actual capacity to be used. So, essentially this stoichiometric time breaks the mass transfer zone into equal areas which is like A2 versus the unshaded area in the plot. So, this breakthrough time can be related, sorry, this stoichiometric time can be related something like this. So, this represents the shaded area of A1 plus A2. So, this if the mathematics of this integration is done, of course, the first part is straight. So, this area A1 is 3.65 into 1, and if you work out this from this profile, the area under the curve on the other side, this would be 1.55. So, this total gives you a value of 5.2 hours. So, this is the the capacity of the bed, or the equivalent time it needs to attain this actual capacity. So, in fractional or the actual bed capacity, that is used here is at breakthrough is 5.2 divided by the breakthrough time it needs, that is 6.9 in this case. This turns out to be 75% or 0.75. So, please note that here, considering the actual bed capacity is at 75% compared to the ideal bed capacity, if there is a constant wave constant wave front that is produced at the stoichiometric, sorry, at the breakthrough time, in that case one would get a much less bed capacity of 52%. So, now in this case, considering this idea of the LES and the LUS, we move forward, and let us say that if the lab scale or if a pilot scale unit is like 14 centimeter long, what is the length unused portion of the bed at breakthrough time? Now at the breakthrough time, the fraction of the bed which is unused, in this case comparing this portion of the sigmoidal curve and taking the half value at that zone, so which represents that 1 minus of 75% of the bed which is used times 14 centimeter roughly gives us the value of 3.5 centimeter. So this is the length of the unused portion of the bed. Now the length of the portion of the bed, or the equilibrium part or the equilibrium section, is actually the total length minus the length of the LUB, because we only segregate this entire bed. So in this case this entire bed is actually segregated into only two parts, unused portion and used portion, where while calculating the unused portion, we are considering the time when it reaches the breakthrough at halfway the value. So let me once again re-emphasize this. So this C C out by C in with respect to time, this is the problem that we are working here, and in this case this is split at halfway here, and that is the point we are considering, that below this portion can be used for the this equilibrium section, and this is the portion for the unused portion of the bed. Of course this diagram is not with respect to x but with respect to time, but in this zone or in this period or whatever the capacity that is utilized in this portion of the bed represents the fraction of the bed which is already utilized, and whatever is unutilized is from this breakthrough analysis of the curve that we have seen in the previous slide can be worked out. So in this case this is the equilibrium portion is 10.5 centimeters. So this is 14 and this is 3.5. So if you subtract this, then the unutilized equilibrium section is 10.5. Now the important question or the scale up question that is posed here, that if you want, if a higher breakthrough time is desired, let us say instead of 3.65 which is the previous case, now we want a new breakthrough time of 7.5 hours, how much longer the bed should be? Of course we say that diameter and flow rate is kept fixed. So in this case it may be noted that currently we have the LES portion as 75 times of 14 centimeter as 10.5 and LUB is 3.5, and that makes the total of 14 centimeter. Now we want this breakthrough time to be increased from 3.65 to 7.5. Then how will we calculate that? So in this case we will use the theory that this ratio of LES to breakthrough time is essentially constant. So which means the LES of the new state represented by star with respect to LES at the current value is equal to the this time TB at the this target value or the breakthrough time with respect to the current state would be constant. So in this case the new LES that is desired is unknown. The existing LES is 10.5. In this case the new theta new breakthrough time that is asked is 7.5, and the existing breakthrough time was 3.65. So with this logic the new LES is 21.6 centimeter, right. Of course to this the unused portion of the bed also needs to be added, and this unused portion of the bed for a particular this adsorbent system provided flow rate and diameter are not same is constant or is same, that is 3.5 centimeter. So if you go back here, so this is like current situation and this is like the desired situation or the scaled up value. So this is for the case of when the breakthrough time is 3.65 and this is when the breakthrough time is 7.5. In this case the LES is 21.6 centimeter, LUB stands at 3.5 centimeter. The total bed length becomes 25.1 centimeter. So this is how you can scale up or you can work out what would be the scaled up length of the bed, provided you have the information of the breakthrough for a smaller bed with respect to time. So this is so the LUB, this is an important point I am saying, that LUB is of the same length that is to be added for any scaled up system, because the LUB is essentially is the portion of the unutilized part of the bed which actually takes up the portion when the breakthrough curve starts to rise. So in this case the fraction of bed actually used is also increased. In this case this is 21.6 divided by the total length of 25.1, and this is substantially higher compared to the previous value of 75%. In this LES I would like to make a bed mass balance. If Q is the flow rate of the stream, C is in the concentration of the adsorbate species in the fluid, and this is the breakthrough time. So, this represents the amount of material that has gone into the bed from the solution phase. This is the equilibrium Q E that is loaded. This is the density of the bed, this is the cross section of the bed, and this is the length of the equilibrium section of the bed, where actually this this mass is getting captured. So, this is the volume of the equilibrium portion of the bed multiplied with the bed density gives the mass of the. So, this gives us the mass of adsorbent in the equilibrium portion, and multiplied with QE, the equilibrium value tells us that how much of the amount of the solute is in the solid phase. So, whatever is this solute that is incoming into the system is actually taken up by the adsorbent. So, that is the outlet concentration in this case close to 0 or almost 0 value, because there is always some adsorbent which is taking up the this species, adsorbate species from the system. Now, this is unlike the scenario in a batch where the equilibrium concentration is in the solution phase is non-zero, but here the since the adsorbate the adsorbent phase is in excess with respect to, as long as the bed is unsaturated, is in excess with respect to the amount that is coming from the incoming solute or the incoming stream. All of these species is getting adsorbed by this bed. This is the whole idea of the fixed bed adsorption, and from here we can do this mass balance. So, next I am going to talk about what happens when we have the Klinkenberg when we have the non-ideal scenario. So, this non-ideal adsorption happens. In this case, the breakthrough curve stiffness is slightly reduced and it takes the sigmoidal shape. So, in this case, the this bed dynamics can be represented by the mass transfer, this species transport equation. So, considering a differential volume, differential length of delta z and differential time of delta d, you can just quickly make a mass balance, that this is the bed porosity, u is the, this is like the simple mass balance of in minus out equal to the accumulation plus the disappearance due to adsorption. So, this is the flow rate or the linear velocity UAB, u, AB is the area and C is the concentration of Z. So, this is equal to at a particular location Z, and then you have at Z plus delta Z, which is equal to epsilon B AB delta Z del C by del T. This is the accumulation term, and this is the disappearance term due to adsorption. It's very similar to chemical reaction. dq by dt, right. So, considering dividing by epsilon b a b delta z and taking limit delta z tending to 0, we get the differential equation as the classical species transport equation. Please note that this Q is like the volume average, but if you are considering it to be the mass average, then this has to be multiplied with the density of the bed. So let us multiply that with the density of the bed. So in this case now, then Q represents the mass average adsorbate loading per unit mass. So of course you can use the linear driving force equation. So and considering isothermal linear isotherm, that Q is equal to K into C, I will write this as KL, and using a linear driving force model, this dq. So the internal mass transport resistance or the diffusion or the intraparticle, these things if we ignore, or if that can be considered to be negligible, then you can use the this linear driving force relation, and dq by dt would be like the mass transfer coefficient kf, the equilibrium coefficient kl for a linear isotherm. Of course for a non-linear model this would be different, C minus C star, where of course C star is the solute loading at the equilibrium concentration and Q is the average. If you want to write in, if you do not want to consider for a linear isotherm, so in general the dq dt relation stands as kf into q minus q star minus q. This is something which we have already discussed in the last week lectures. So this is the generic form. Now for this is applicable when we are considering linear isotherm models. Now for the case of this solution of this equation, the solution of this equation, this analytical solution, I would say analytical approximate solution is given by the Klinkenberg relation, where this C out by C in is given by this formula. So for details you can look into the famous Klinkenberg paper. This represents, this parameters represents and this, so this is some sort of a dimensionless distance coordinate. So please note that C would be a function of, should not say C out, but rather C is a function of Z and T, and the dimensionless time is represented by this. So this is like dimensionless time coordinate, but this is corrected for displacement. So t minus z of u represents the characteristic dimension of the time, and this ERF represents the error function. So ERF of x is generally defined as, this is a classical mathematical function. Is the error function. So these are this epsilon and z are like the coordinate transformation both for time and distance. So I must add this density also here for the bed, which I missed. So please note that in the dimensionless distance coordinate, there would be the value of this dimensionless distance dimensionless sorry, the density that would be also used, and appropriately the value of the this coefficients KL is the unit in the isotherm equation. So these Klinkenberg equations actually helps in relating or trying to get an idea of the mass transfer zone or the the sigmoidal shape of the wavefront in the non-ideal case, but this is like solving for analytically or numerically solving the species transport equation. A complete equation, the solution of that equation in terms of the Bessel function for heating etc. is also provided by Anzelius, but these are highly complicated techniques, and that is something we would not be focusing too much on this course. But I wanted to give you an idea about the Klinkenberg relation that can be useful. This is an approximate relation, of course, that is useful to work out the nature of the solution profile in this case for non-ideal situation. So with this I would like to close the lecture for today. In the next class we will see other semi-empirical and detailed first principle based models for the modeling the performance or the solution profiles species concentration in the fixed bed adsorption column. Thank you. I hope all of you found this lecture to be useful in the design and scale up of fixed bed adsorption, particularly in the case of some approximate situations or some assumptions of limiting mass transfer resistances or negligible mass transfer resistances. Thank you. Hope you all find it useful.